So our last little bit of revision in preparation for Year 12 Specialists is going to be looking at our vectors. Now, it's important that we do spend a little bit of time revising our vector concepts from Year 11 because, again, if you read the examiner's reports, and again, I'll give you all this information as you go through the year, the examiners have commented that students are very good at the basic vector ideas, but they struggle with the actual conceptual understanding of it and actually applying it. So we're going to spend a little bit of time today just reminding you of those ideas and pointing out a few things that you'll see this year in Specialist 11. So there is a separate booklet for this. It starts off with a little bit of a revision of your Year 11 concepts and talks a little bit about some of the ideas that you'll see in Year 12. So, a reminder that a vector here is obviously a quantity that has a magnitude and direction, and we've got it with an arrow. And we've got some vectors here, and we can say various things about them. So, the blue and orange vectors have the same magnitude, but not the same direction. Our blue and purple vectors have the same magnitude and direction, so they're equal vectors or like vectors. And our blue and green vectors have the same direction, but different magnitudes. So they're parallel vectors. We know about our vector addition. So we know that if we want to add two vectors, then we can use our parallelogram property. And again, that's all from Year 11. We know that if we have the opposite of a vector or the negative of a vector, that's just the vector going in the opposite direction. And we know that we can multiply our vector by a scalar. There's a couple of examples here which we won't necessarily go through because I'm just mindful of how long this video will be. Again, notation. For some reason, I've put the little tilde symbol above. That's just because I'm doing it off the computer screen and sometimes a little bit hard. But again, it's important that you are very careful with your notation. The examiners have commented that they are concerned about the notation that specialist students are doing. If you just write I without a tilde, they're going to read it as the complex number I. They're not going to read it as the unit vector or the I component vector. So make sure you are very aware when you're talking about a vector, when you're talking about a complex number, etc. So we've got our vector in component form. So we know that we've got 3i plus 2j. We know that if we're adding vectors that are in component form, then we can just add the I components and add the j components together. And we can think about what that means geometrically as well. We've got the magnitude, which we know is just using Pythagoras. We've got our unit vectors. So we know that our unit vector, which is denoted with the little hat symbol, is just the vector itself divided by the magnitude. So that gives us a vector which has length 1. We've got a position vector. So of course a position vector is a vector where its tail is at the origin. So we've got there A is OA, B is OB, and there's a slight error here because that should be the opposite of OA. But we can say that AB is just going to be the opposite of A plus B. So again, we're using our vectors here. We're using our rules of vectors to actually represent these quantities. And again, have a think about how would this relate to complex numbers as well? What have we seen that's familiar with complex numbers? When we add our components, that's the same as what we do in complex numbers. We can we use a complex number to represent a vector? Is there connections there? So that's all things to start to think about because that's what they want in the course. We'll also talk about the dot product. So we know that if two vectors are perpendicular to each other, their dot product is 0. If they are the same vector, if they're equal vectors, the dot product is 1. And we can also define the dot product of two unit vectors. Notice what we've said here, they're of unit length, as the angle, cos of the angle between them. Obviously, we can be a bit more general. And when we do we can do it in the component form, and when we do our dot product, we get an actual number here. So it's important to remember that dot product gives us a number. It's also called scalar product. Reminder that you can do dot product on the class pad as well. In the complex number video, we showed you under action, you had vector, and you would have seen in that list there was a d dot p. There was also a norm, which gives you the magnitude. So again, these are all skills that we'll revise in year 12. We can also define the dot product as the product of the magnitudes times by cos of the angle. And we know that dot product has several properties. That a dot b is the same as b dot a. We could take out the scalars out the front. We can expand it out, etc. So again, all of those dot product rules we'll see again, but it's sort of assumed that you know those rules already. So we're going to revise them, but we're going to move through them much faster. Now, the main aim of the Specialist 12 course is to look at the applications of vectors to three-dimensional situations. So essentially, 3D vectors behave in much the same way as 2D vectors, except we have a third component. So you have exactly the same conventions. We have an I and a J component, but we just put that third component, that third dimension is just going to be K. So we can write it as I, J, and K. We can write it in these, the angle brackets, or we can write it as a column vector. Again, you pick the notation that you're comfortable with. But again, if a question's been presented in a certain way, I would be presenting my answer in that same way. Doesn't matter about your individual working, but I wouldn't be swapping between notations regularly. Stick with one notation and use it for the whole question. Magnitude. Well, how does magnitude work? So, magnitude of a vector is just going to be using Pythagoras. So all we just do is we just add on the square of the third component there. Dot product. How does that work? Well, if you're now thinking about it, that's going to work in exactly the same way. Dot product of A and B is just going to be the product of each of those of the I components plus the product of the J plus the product of the K components. And again, it's just going to measure the angle between those two vectors there. So again, everything just flows from two dimensions. Now, there's a bit of calculator screens here, which is in the booklet as well. Unfortunately, it's the old screens for some reason. So you can define a vector either using your column or row matrices. You could also use the square brackets, which are on the Math 3 keyboard. You could do the magnitude, which is the norm. So that allows you to do that. You could do the dot product, and you can do the angle. So if you're going to do angle and dot product, a reminder that you can put in both vectors, but you've got to put a comma between those two vectors there. Now, there's a couple of examples here which we'll have a quick look at. First one's calculator assumed, second one would be calculator free. So if we want to find the angle between vector u and vector v here, so here's our dot product that we're going to use. We can substitute in what we know. Well, we could do the dot product of v and u, or u and v I should say, in the numerator using the component form. Now be careful here. This is one thing that they like to do, is they like to drop off one or two of the components. So just don't go blindly through and go 6 times 3. There's no I component for u. So make sure you're aware of that. Over the product of the magnitudes. And you get your angle, you get your cos theta is equal to that. And then we can find the angle there. And again, we can do that on the class pad. Second one, as I said, will be calc free. Find the value or values of theta of alpha if the angle between these two vectors is 60 degrees. So again, we're going to use our dot product. We're going to substitute everything that we know in. Now, this is again, as I mentioned in the methods videos, you've got to be very good with your algebra here. And again, if this is calc assumed, easy, because you can just throw this straight in your class pad. If it's calc free, you're going to have to be able to rearrange this equation and solve for alpha. Well, you'll notice that in the numerator here, the alpha actually disappears, so we actually just land up with 2. We can identify that cos of 60 has an exact value of 1/2, so we can substitute that in. Now, just take a little bit of time in rearranging this equation here. I'll just go through this a little bit fast here. So what I've done is I've written this over I've written an equivalent fraction here. So I've got 2 in the numerators. Because I've got a fraction equal to a fraction, I can then do the reciprocal of both sides, and then they're over a common denominator. And then I can go through and actually square both sides and solve there for alpha. A reminder that scalar projection and vector projection, which you did last year, is actually still part of the course. It's not specifically mentioned, but it's in that catch-all first dot point about revising all of your year 11 specialist work as well. So a reminder that the scalar projection, well, scalar projection of u onto v is just going to be the vector u times dot producted with the unit vector of v. So I can find out the unit vector, and again, class pad, no class pad, it's up to you how you want to do this. I can use the class pad to work out the magnitude, or I can do that by hand. So that means that I'm looking at the vector u, dot product with the unit vector for v. So there's my vector v times by 1/4, because I want to get it as a unit vector. Now again, I can do that on the class pad, or I can do that manually, and I get a dot product there of 4. So that's my scalar projection. Now to get my vector projection, well, the vector projection is just going to be the answer from part A, the scalar projection, times by the unit vector for v. Because remember, the dot product is just a scalar. So I can do that. I can just multiply this answer. Here's my unit vector for v. I can just multiply that by 4, and I get that answer there. Now, you might notice here that the answer here is v. That's because there's something very interesting going on in this case here. That's not the general case. So I'll let you explore that a little bit more if you want to. Last little part for this video is we're going to have a look at the vector equation of a line. This is actually done in the course. We will spend a couple of lessons on this, but if you do want to explore some of this idea, then we'll start to talk about it here just briefly. So what we have here is we have our point A, and it's got coordinates 2, 1, and 1. Well, I can write A as a position vector, obviously, 2, 1, 1. And let's say I've got another point B, and that has coordinates 3, 2, 0. Now, it's very hard to see in this 3D situation that they are, where they are. But again, that's what we'll do in class. We'll actually get some 3D models, and we'll actually show you what's going on. Right, if I want, I can draw in a vector, AB. But the reality is I can actually extend that vector AB, and I can actually form a straight line. So what I might want to be asking is, well, what's the vector equation of that line? Is there an equation that allows me to find the position of any point on that line? Because that's what the equation of a line does. If I give it a certain value, for example, if we go back to year 8 and 9, y is equal to mx plus c. If I give it a certain value for x, I can find out the y coordinate. So this is going to say to me, well, if I put in a certain parameter, can I find out where that point is on the line? Or can I work out if that point's on the line? So what I'm going to say here is I've got my vector AB, which is 1, 1, negative 1. Well, that vector is parallel to the line. So I'm going to just put my vector, I'm just going to separate that out so it's a little bit clearer what's going on. But as that vector AB is parallel to the line, then what I could do is I could multiply that vector AB by any scalar to give me any point on that line. So what I'm going to call that vector here is I'm going to call that a direction vector. So that direction vector D is parallel to the line. And as I said, if I want to find the position of C, well, what I could do is I could say, right, well, OC, the position vector of C, is just going to be OA, where A is a point on the line, plus AC. But hang on, AC is that line, and that vector is parallel to that direction vector. So I can just say that AC is going to be a scalar multiple of that direction vector. So what that means is that if I want to find the vector equation of a line, I've got a fixed point on that line, let's say point A. So I've got OA here. R is a variable point on the line. So R is any point on the line. I have my direction vector of my vector here, which is D. So I can say that OR, the position of any point on that line, is represented by OA plus AR, but AR is just a scalar multiple of that direction vector. Hence, I can say that AR is lambda times by the direction vector. So therefore, I can say that any position on that line R is represented by a fixed point plus lambda times by the direction vector of that line. So that allows us to find the vector equation of a line. Now, I'm only introducing that to you. There's no exercise in the notes about that. There's no expectation that you're going to spend some time on that. If you want to go further, there are some examples of those. And I'll quickly put the solutions up. And if you want to look at these, you can pause the video. And then we get into vector equation of a plane. Now there are notes for that. I'm actually going to stop going through this PowerPoint at that stage there, but you can have a look at that if you want. The only other thing that I'll say at the end of this video is one thing that you can be doing is there is some revision of your vector proofs. And again, vector proofs are now extended to 3D situations, but you can always have a look at the vector proofs that are here in the exercise, which are nearly all 2D situations. And there's also at the end here some revision of our Year 11 skills. So it's important to start revising those Year 11 skills and start to get in preparation. We'll stop the video there because we've probably done enough. Hopefully we're back next week and we'll get stuck into all of the complex numbers and function work next week.